Now, when I come and teach courses, I never really know the experience level of the people, and so I put in a number of exercises and things just to uh, make sure we're uh, all kind of together. Now, I think you guys are experienced enough that you understand well logs, so in case this was a beginner class, I brought a couple of logs here to do uh, net net pay characterization, but I think you guys are experienced enough to do that, so I'll give you the answer here. The what I was gonna ask you to do was it, what I would ask you to do is, what is the net sand here? If this is a gamma ray log, gamma ray cutoff, and to estimate the net sand. Well, you guys know how to do that, I'm sure, so I did it for you here. It's about 10% up here, about 30% here, about 20% net sand there, and about 15% there, a couple of percent here, and that all totals up to about 75 feet of net sand out of 100 feet. So in percentage wise, the sand content is 75% net sand in this 100 foot of gross interval. So that's that, and I presume you all could have figured that out yourself. And so I'll move on. Talking a little bit about reservoir quality now, porosity and permeability. One of the things that bothers me a lot when people are building models, geological models for reservoir simulation, is the upscaling that has to be done. And I realize why one has to upscale. If you didn't upscale your reservoir properties, be too big for your computers to handle. Us geologists, we love to take lots of data. And you take all this data and spend all this time and money, and then after you build the model, a lot of that data is gone. It's been taken away. So you lose accuracy of your comparison with your real reservoir when you do that. And because what happens is there's a very pronounced control, particularly of permeability, on by grain size of sediment. And so here we have, for example, a gamma ray log is getting finer and finer upward, and that's because you have, during deposition of this meandering river, you'll have different sedimentary phases that are a function of stream currents and things like that. And typically what you find in a meandering river sequence is what we call fining up. The grain size gets less and less, and that actually controls permeability. So permeability varies with sediment grain size, and even after cementation, you'll still get some remnant permeability that'll be a function of the original grain size. So, so at any rate, high permeability down the base where the grain size is coarsest, and low permeability upward where the grain size is finest. So this is one of my favorite slides that I like to use that shows the effect of this in very simple terms, where we have a sand body in yellow with shales bracketing that on both sides. So in this particular example down at the bottom here, we have a very sharp base for a gamma ray or SP log, and we get this fining upward trend. which is shown by these black dots. And the size of the dot, the diameter of the dot, is a function, is grain size. So you see the grain size is getting finer as you go up. Well, if you now do a water flood, let's say, and what will be, if you do a water flood in here, what will be your remaining oil saturation after the water flood? Is it going to be, is your water going to flood uniformly, or is it going to finger, or is it going to segregate into units based on permeability? Well, it's going to mainly do that, the last one, segregate according to grain size. So if you look over here at this little stair-step sort of pattern, this is the oil saturation in percent, remaining oil saturation after water flood. Okay, and what you see is that from the bottom to the top, you have an increase in your oil saturation. Why is that? Because the water, when you injected water for your water flood, the water sought out the most permeable zones on the bottom and did a very good sweep efficiency, but not a very good sweep efficiency in the finer grained, less permeable part of the reservoir. And this is something that is often left or upscaled out when you're doing a reservoir model. You'll say assume a constant permeability, for example, when in almost all cases that's not true. You get this sort of gradation as a function of grain size. Well, here's another example where we have an upward coarsening in grain size. By the way, I should mention for those of you that are engineers, geologists always describe things from the bottom to the top, okay? And the reason we do this is because that's the way it was deposited. Now, engineers usually describe things from the top down, because that's the way they're drilled. Okay, so I'll be talking from the bottom up. So at any rate, so here's another example. It's getting coarser grained upward, shown by the gamma log, and cleaner. And here you see the remaining oil saturation after the water flood, and you see now just the opposite trend, that you've still got a lot of remaining oil saturation below and much less above, because you had a better sweep efficiency in the more permeable upper beds. So something when you're upscaling, something to think about, trying to minimize the upscaling process, particularly in permeability, is very important, especially if you're modeling fluid flow. Okay, well, let's look at, say, an analog of a reservoir. This happens to be in Houston, Texas. This is the Hess building. Hess is an oil company, H-E-S-S. And I like that as a analog to a reservoir because you have rooms, and you can consider the rooms in this building as the sands. But you've got floors and ceilings in these rooms, so floors and ceilings, and you could consider those as reservoir seals. So they're going to compartmentalize the rooms, this room, the room next door, and so on. You've also got walls here, and the walls would be your either a ceiling fault or a stratigraphic pinch out. But not all rooms are the same. You've got different types of rooms with different purposes. And so that you have to factor that in as if you're going to build a reservoir model. And if you have well logs, you can, with well logs, you can often determine the reservoir sands, the seals, and the pinch outs and fault traps and things like that. But on seismic, I want to just point out that you don't see often at that particular scale. So here's a seismic wavelet, and that wavelet might cover this entire building. Okay, so you do see the reservoir by an amplitude anomaly, but you don't see the roofs, the floors, the ceilings, and the walls. Okay, so this is why reservoir characterization is very important. Now, what I hear all the time, people saying, well, we'll understand our reservoir better if we shoot seismic. Okay, we gotta have a 3D seismic survey. But keep in mind that that there's limits to resolution of a 3D seismic survey, so that may not give you all the answers because of that resolution. And so you have to really apply your knowledge to the geology from well logs, or if you understand the depositional system, you can use that to help build a model and so on. So just keep that in mind, that seismic, although very good, is not perfect, and you miss a lot when you shoot the seismic. So reservoir performance, the importance of that is reservoir performance is often governed by features that are beneath seismic resolution or detection. We call these subseismic scale. So here you see a map that's based on well logs, okay, and the map that you have, it looks continuous. Looks like you have a single sand body there of variable thickness, okay? This is an isopac map, but in this particular case, 3D seismic was shot over the area, and it was very useful because what you saw then was a highly compartmentalized reservoir. It wasn't like this at all, but the 3D seismic showed that you had all these isolated or semi-isolated sand bodies. So when you drilled a well here, for example, it was a dry hole. A well here was an oil producer, and so on. And it showed you that there were still areas where you could drill new wells in compartments that had not been drilled. For example, probably this nice long sand body here, sand body there wasn't drilled, one here, and so on. So the 3D seismic in this case was very useful at actually giving you a good picture of the reservoir, much better than if you thought it was a single sand. And the giveaway here, how you can tell that is that you've got these dry holes that are within the reservoir amongst all these black dots, which are oil wells. And so you have to try to explain why you've got no production in those two wells. The reason is that one was drilled where there's no sand, or virtually no sand, and these were drilled right, this one here, that was drilled right on the side, still pretty sandy, not quite sure why. Well, you're on the edge of a sand body, and then down here, you're really outside of the sand body. Okay, so you don't get any production from that well either. So, important, seismic is important, but still not the cure-all for everything. Now there's a lot of what we call seismic attributes, and none of you are geophysicists here, so I don't know what your background is, but geophysicists spend a lot of their time, particularly research geophysicists, spend a lot of their time trying to reduce or improve the resolution features you see. And they've developed a number of mathematical equations that takes the amplitude data and converts it into other properties. So we call these seismic attributes. And this is just one of them that I like to use. It's very useful. This is a cross-section where you have an anticline or an antiform, and a syncline or a synform. And what happens when wavelets hit the anticline, they disperse out. They're reflected in an outward manner, like you see with those arrows. By contrast, when your seismic hits this zone here, where you have a syncline and is reflected back, the reflectors converge, okay? And so you can take that and manipulate it mathematically and come up with images. And in this case, we have a channel. What you're looking at now is a horizon surface from a 3D seismic area. And here we have a channel with the red being the edges of the channel, the parts that stick up. Okay, so these would be the antiform type features. So that defines the channel itself by imaging the size of the channel. Now, here, this one in blue is actually the synform here. And so if we were to pick this up and overlay it on this one, it would overlay right in the middle. Okay, so you've got now a clear image of your reservoir. You know where the flanks of the reservoir, channel. So you know where the flanks of the channel are, and you know where the interior of the channel is too. Now you can apply other attributes to determine if it's sandstone or shale, for example, but that's not shown here. So this is just one example of improvements that are made in imaging, seismic imaging, by developing these seismic attributes. We're very fortunate at Oklahoma, University of Oklahoma, to have a professor by the name of Kurt Marford, who is a world expert, wrote a book on geophysical reservoir characterization. And he does a lot of, him and his students do a lot of this work with seismic, developing these very complex mathematical formulations that allow you to do things like this. Now, as I say here, the usual goal for the geologist anyway is to build a geological model that you think is similar to the reservoir. And you can input into your three-dimensional model any properties that you want. For example, here's a 3D model of sedimentary facies. The different colors represent different types of sand bodies. So you can model that. Here's a model of porosity, where the different colors represent different porosities. And your water saturation model here, which shows variations in your water saturation. Now here, this shows if you apply, or when you apply some sort of constraint to your model, what the effect can be. Here's a model here that's built with a constraint that the reservoir has 35% sand, okay, 35% sand. And then you can run a series of iterations of your model, all having 35% sand, but what's different is the locations of the sand. Sands are in yellow here, shales in black. So you run all these iterations, and this one here was, I think, the 90th iteration. You can do this very quickly and then get different distributions within your model of that 35% sand. Then you have to go back to your geological knowledge to figure out which one of these iterations most likely represents your reservoir. So it may be this one, where you've got two sand bodies like that, or it may be this one, where you've got one sand body, always 35%, but what is important here is that the geographic location, of the sand bodies is different. And of course, that's going to affect where you drill your well. So, looking now at the time aspect of reservoirs, usually what you're looking at is cash flow on the vertical axis here. Negative cash flow meaning you're spending money, positive cash flow meaning you're making money. And this is time from exploration all the way to maturity and abandonment. Now, most of the time, you do a reservoir characterization kind of in a traditional manner. You look at whatever data you have, usually rather quickly, and you might end up with a curve that looks like this, where when you make your discovery, and as you're delineating your reservoir, you are spending money. You're not making any money, you're spending money. But then at some point, when you go into development then, you start making money, and you'll maximize your production after a certain amount of time, and also you try to minimize your operating expense. And so at some point in time, your reservoir starts to decline to a point of abandonment. Now, if you do a more detailed reservoir characterization, although it involves more data and more time to do, you can often increase your productivity. Like I said earlier, even a 1 to 5% increase in your productivity in a large field, that's a lot of oil or gas. And so this black curve here is one where you kind of accelerate your production. You go into production as you're still completing your appraisal phase, and then you start making money. If you do a good job at your characterization, you can maximize your production even higher than with a kind of a standard characterization, and quite often then you can keep your reservoir going for a much longer period of time before you defer or abandon the reservoir. So this is an example of just value of doing a good reservoir, a good detailed reservoir characterization. Okay, by the same token, the more data you get, the better will be your reservoir characterization. However, there comes a point where, at least in terms of using data for characterizing your reservoir, that you don't need so much data any longer. And that's what's illustrated in this diagram, that with time on the horizontal axis and estimated ultimate recovery on the vertical axis, and in millions of barrels. And when you first start out in the exploration phase, you may make a discovery. You have one well, so your range, you can make an estimate of the amount of recovery, but the range is going to be very large. maybe anywhere 20 million to 80 million barrels of oil, a wide range because you have very little data. Now, as you go through the appraisal phase, you reduce the uncertainty. So now your uncertainty is somewhere between 25, maybe 65 million barrels of oil after you've gotten enough data to do a pretty good reservoir characterization. But then as more wells are drilled during development and production, you gather more data. So there comes a point in time where you know everything about the reservoir, but by that time you're going to abandon the reservoir. So you never get to this point, or usually you don't get to this point. But as you get more data, you're decreasing the amount of uncertainty in your volumetric calculations. And this might be the average case, the solid black line here. So just this diagram showing how drilling wells and gathering data can improve your estimate of the volumetrics of your reservoir. Well, shown here is, for example, the case here where you have one well drilled. We're looking down at a reservoir now. We have one well drilled, so we're going to be up in this range over here. Here we have 5 wells, so that may be our appraisal phase, so we're over here. And now drilling 9 wells, we're going to be somewhere over here. And then at this phase, we've drilled up the whole field, and we might be somewhere down in here. So the value of data, very important. Also important is your calculation of your resource versus your reserves. What you want to know is the reserves. That's what you can get out of the ground at present conditions. When you start out with a resource, this is your total accumulation of hydrocarbons. So here's your resource. You start out with this much of a resource. But let's just say that only this much is accessible to exploration. So you now lose, or you never know that you had this extra amount in your original resource. It's just not accessible for one reason or another to exploration. So you identify your reservoir, but you may identify part of your reservoir, but not all of it. So let's say we don't identify this much of our reservoir. So now we're down to this much of our resource that we have identified. Now, technology plays a role then in that some of that reservoir might not be technically possible to exploit, and only part of it might be technically exploitable. And so now we've chopped off some more of our reservoir, and then the economics come into play. So perhaps at whatever the price of oil or gas is at a particular time, it might not be economic to produce this much of the reservoir, and it might be economic only to produce this much. So your final reserve then that you determine is this much, even though you started out with a much bigger resource. And the things that affect that are accessibility, the technology, and the economics. And quite, I think as we've all learned in the last couple of years, is really the economics is the driving force of everything else. If you don't have economically profitable, a lot of this other work isn't done at all, or done very minimally. Well, where have we learned that the best is a picture here showing crude oil prices as a function of a year from 2010 through 2015. In the year 2011, right here at this peak, oil was $113.39. And in August of 2015, it's down to $45. So a lot of this work that would be done here is not being done by a lot of companies. They've slowed down their work, they've laid off people, things like that. So here we have kind of a general curve or a general trend where you have some ups and down, ups and down. This is the nature of the oil and gas industry. What I tell my students that want careers in oil and gas, I tell them it's kind of a rough road of ups and downs, a bumpy road, but still it's a good path for a good career if you have patience to wait out the bad times and wait for the good times, because just the nature of the industry is cyclic. So and here's some of these up-down cycles. Now this is very dramatic, this one here. Things are getting a little bit better. I think we're up today up at about $50 a barrel. But most people would say we're never going to get up to there again, up in the hundreds. So that's had some positive effect actually, because one of the things this low price of oil has done is it's gotten the companies to become more efficient. And they've had to try out new technologies, whatever it takes to make them more efficient. And this curve is mainly for shale gas or shale oil. And what was unprofitable at $45 a barrel back in 2015 now might be profitable, okay, because of better efficiency. Or if the price goes up to $50 a barrel, that's even better. Or we all hope that it goes higher than that. Well, I'm going to spend a couple of slides here on unconventionals now. Here, this one. So we're about here now. And price of oil somewhere, well, excuse me, we're in 2016 now. Sorry, this was when I last, we'd be out over here somewhere now. Okay, well, I'm going to spend just a couple of slides on unconventional resource shales. And because they are becoming a bigger and bigger part of our energy mix. Now, my understanding is in Bolivia, there's not any exploration for oil or gas shales, but there will be undoubtedly in the future. Is where a lot of companies are putting a lot of their resources now into that. So this diagram here just compares conventional reservoir. I'm going to go to highlighter. A conventional reservoir may be an anticline there, or a stratigraphic pinch out, like you see here. But the unconventional gas, for example, doesn't require a structure. The gas is the shale is its own reservoir, and it's its own source, and it's its own seal. well, so you don't really need a structure. So it's a different style of exploration than if you were exploring for conventional reservoirs, where you have pinch outs, stratigraphic pinch outs, and structural reservoirs. You don't need that in unconventional. So here's just some prediction then. Here's the year 2010. We're now here at 2016. This prediction was made in 2010. Back to this. This prediction was made in 2010 that in about 2005, that's really when the shale boom started to really become very important. And so you can see the amount of shale gas that has increased between the year 25 to 2010. And now we're up here at 2016, and we're producing more shale gas, even though the price of gas, at least in the US, is very low, and that has hindered production because of a very low price of gas. But still, it's expected that the major source of gas, for example, all natural gas, will be from the shales. And that's why I say in Bolivia, it won't be too long before you're starting to explore for and finding and developing. I have no doubts there's a lot of good shales in Bolivia that are potential reservoirs. We've looked at shales in Venezuela, in Colombia, China, Argentina, several in the US, and I'm sure Bolivia has potential as well. We've got a lot of experience. In the last 5 years or so, all of my group of students and I have been doing is working on the shales because they're so important. So here we are, unconventional, where we have large volumes, very aerially extensive, these shales, but difficult to develop because they're so fine-grained. So as I said, because of that, you have an increased cost of recovery down when you get into here, and you need advanced technologies. In the case of the shales, horizontal drilling and artificial fracturing. Now in the US, this is the distribution of shale plays, both gas and oil. We do a lot of work right in here in this one called the Woodford, but the Eagle Ford down here is quite large. Barnett, quite large. Marcellus Shale, very big. Bakken Shale is partly in the US and partly in Canada, is very big, and then there's a number of others that are scattered around. And the more people are exploring for shales, the more they're finding. So if I were to show this diagram in another few, this is 2011, and there's already some more on here that aren't on this map. And if I were to show it, say, in 10 years, there'll be a lot more. And our knowledge of how to produce them will be a lot better. The top 7 shale plays in North America, both oil and gas, here's a listing of them. They may not mean much to you. They're just local or North American names. The Woodford, Bakken, Eagle Ford, Granite Wash, Marcellus, Niobrara, and the Permian. The Permian is the big one now, huge, several billion barrels. The top 7 companies in the shale plays are listed here: EOG, Pioneer, Continental, Cabot Oil and Gas, Noble Energy, Anadarko, and Range. Now, a few of these companies have changed since 2012, the 2012 listing. But basically, today, in the U.S., this is a plot of the U.S. oil fields, the estimated recoverable resource. And the top one is what I called in a previous slide, what I called the Permian, this one right there. And it is tremendous, huge. And so you see an estimate here of the recoverable resource, and it's larger than anything else by far in the U.S. It used to be thought that the Eagle Ford Shale, this one, was the largest, but not anymore. It's still large. Prudhoe Bay Field, I'll talk about when we get into fluvial reservoirs. Prudhoe Bay Field is the 3rd largest now in North America, or in the U.S. It used to be 1st, now it's 3rd. It's been overtaken by the unconventionals. And then we go back in the Bakken Shale, Delaware Basin, that's, the Delaware Basin. And then most of these others are conventional sandstone reservoirs. In fact, they're all sandstone reservoirs, except maybe, let's see, maybe not the Delaware Basin, I'm not sure. So you get an idea of the significance of the shales, oil and gas shales, for the future, and that's going to be the trend. I teach at the University of Oklahoma. I teach a shale course, mainly geology, but I input some engineering and geophysics as well, and petrophysics. So, and I have a lot of petroleum engineering students that take the course. Be happy to come down here and teach the course. So the 2 technologies that really led to the shale boom are horizontal drilling and hydraulic fracturing. Now, both of those technologies have been around for a long time, but they were only merged together with shales maybe 15 years ago by one company, mainly Mitchell Energy, and they combined, they knew that they had a shale called the Barnett Shale, and they knew that that shale was had a lot of gas in it at first, and so they tested out for a couple of years, combining horizontal drilling with hydraulic fracturing, and it proved very good. So they went and improved as time went on, and other companies started getting involved in applying those technologies to shales, and so that was really the result then of the shale boom, as we call it, the oil and gas boom. So here we have some platforms here with series of wells off of each platform. And here we have a cartoon. This is a vertical well going down here, and it's going off horizontally there. And then you artificially fracture once you know you're in the reservoir zone. And so you artificially fracture. Fractures go into the tight shale and open it up so that you can get the gas or oil into the well bore. So those are the 2 technologies that led to the boom. Now, I just want to point out here that fracturing is a major operation, and this is all the machinery and automotives and things like that go into a fracture job, where you have your water, your sand, and your chemicals that are all pumped down to have pressure to fracture the rock. This just shows a little blow up of the fracturing process. You fracture your rock, and the sand, the chemicals, and the water then go through the wellbore and out into the rock. So it's seemingly a simple process, but very costly and very very detailed. Okay, well, moving along in this, just kind of touching on a number of different things. I'm still on my introductory section here. This is a saying that I think applies to reservoir characterization quite nicely. It says, 2 stonecutters were asked what they were doing. The first said, I'm cutting this stone into blocks. The second said, I'm on a team that's building a cathedral. Well, which one do you think belongs in the oil industry? We like to work in teams. No longer do we work alone most of the time. And a reason for that is just each one of our disciplines has become so detailed and involved that no one person knows everything. And so you have to work in a team. So that expression is very applicable to reservoir characterization. Now I want to tell you a little story about a very famous geologist by the name of Robert Snyder. He was probably, we could call him the father of reservoir characterization. He started his career after he got a PhD. He started his career at Shell. And this was at that time, this was the typical organizational structure of the exploration and production company of Shell. They had a manager, an exploration manager, and a production manager who oversaw geologists, landmen, geophysicists. The production manager oversaw the production engineers, drilling engineers, reservoir engineers. And Snyder worked in that organization for some time, but felt that it was not very efficient because there were physical barriers as well as social and people issues, things like that. Trying to trade data between production and exploration was sometimes difficult to do, and things like that. So what Snyder did is he quit working for Shell and he formed his own company called Snyder Exploration. And what he did was he integrated the disciplines into teams. And this was the beginning of this concept of working in integrated teams, where you might have one team with the geologist, the landman, engineer, and geophysicist. Maybe in this team, working on a field that had no geophysics, so you didn't need a geophysicist there, and so on. And so these people would work in these team settings depending upon, one, their expertise, and two, what sort of data they had. And in order to, excuse me, I made a mistake. Snyder did not quit Shell at that time. What he did is he went to the president of Shell and said, I can do it a better way than organizationally than the current structure that you have now, and I can make us more efficient. And he was very highly respected geologist within Shell, and so they said, okay, go ahead and prove it. I'll give you 5 people, different disciplines. You can have your own building, go do your own thing, do your own exploration, do your own development, and come back in 2 years and tell me what the results were, and we'll compare with the way we've been organized for many, many years. And so they did that, and what they found was under the original or organizational structure where you separated exploration and production, they found a number of barrels of oil, and the finding cost at that time was $8.97 per barrel. Well, the other company, Snyder's little teeny company of 5 or 6 people, went and found during that same time interval 2.8 times the number of barrels that were found by the large division at a finding cost more than half of what the finding cost was with the big company, $4.31. And so that was the beginning of the team concept, because Snyder had convinced the company management at Shell to break it out into this sort of an organizational structure. And now since then, most companies work in team settings like that, and it's pretty commonplace, at least the companies that I'm familiar with. This was written up in an AAPG Explorer article as a very good example of integration, where you could actually figure out the value. You can put a cost, a number, a dollar number on the value of integration, or synergism as it's called here. Well, this fellow here, Carlos Bahaman, Colombian student, former student of mine, works for Oxy now, and he at one time put together a chart of geoscience responsibility areas versus reservoir engineering functions. And it's in 3 slides. I'm not going to go through these, but I just give them to you in case you ever want to take the time to go through those. It would take a lot of time to do it right here, and I don't want to spend that time. But here's one page involving increasing reserves, increasing production, developing reserves, safety, sharing, increasing production, safety, sharing, some more of that. And yeah, so at any rate, I give you those just if you want to look at those at some time. Very thorough analysis of the responsibilities of geoscientists and engineers. Okay, I'm going to go through this, and then we'll take another short break. What I want to talk about here is scale. One of the biggest mistakes we make often is in assigning the wrong scale to a reservoir property. And what I mean by that, well, I'll show you what I mean by that here. I originally gave a talk to a geophysical group, but it aimed towards a little more understanding of geology from geophysicists and also reservoir engineers. So there's a number of geological features of reservoirs that control the performance of the reservoir. And I just list these: size of the reservoir, the shape of the reservoir, the internal makeup of the reservoir, the size, the dimensions, whether the reservoir is continuous and connected or not, structural attributes like faults, fractures, and folds, grain size and composition, porosity, permeability, and capillary properties, burial depth and history, and drive mechanism, which is not really a geological property, but all the others are. Well, in this talk I gave to geophysicists, this was a group of theoretical geophysicists that didn't know anything about geology, and so we kind of simplified things down and said, there's three geophysical components: your source, your medium, and your reservoir. And the medium is your geology of your reservoir, so geological reservoir characterization falls into that realm. Well, I'm going to show you some examples of different levels of heterogeneity or scales of heterogeneity. And I'm going to start with the large scale and work on down to the small scale. So at the very largest scale, I'll call that level 1. Okay, level 1. The simplest breakdown, geological breakdown we can make of a reservoir is just whether it's a sandstone, a carbonate, or a shale. Simple as that. So that would be level 1. Now let's just take the sandstone, for example, and go on to level 2. So level 2 is a sandstone, but as I showed this diagram before, there are many different types of sedimentary environments in which sandstones are deposited. So you get a series of deposits on continents, along the shoreline, which we call mixed, and then marine deposits as well. So let's use as an example continental deposits. So let's look at this set of deposits here. So here they are at level 3. We've got fluvial deposits, aeolian deposits, alluvial fan, and lake deposits. Let's look at fluvial deposits as an example of level 4. Well, a fluvial deposit can be either a meandering river type, an incised valley type, or a braided river type. So that's level 4. And now we're getting more and more detail as we go down these different scales or levels. So let's use the meandering river as an example and go to level 5. So level 5 is a meandering river, and it's made up of a number of components: point bars, mud plugs, cut bank and point bar sides, point bars there, and a cut bank side there. If you were to stand on this, this is a nice sandy point bar, and if you were to dig a trench through there, it might look like that, something like that. Or in a reservoir, it might give you a gamma ray response, something like that. Or this one here, which I'll show in another, too small to see, I'll show us in another diagram. So let's go down now to level 6. Well, first of all, the component parts. Okay, now we go to level 6, or excuse me, no, we're still at level 5. And what we see at this scale now is where we're really getting important, where we're getting down to a scale that's really controlling your reservoir performance. Here you see a meander belt. This is a modern one. And you see yellow is sand, and then you see these blue vertical areas here. Those are when there's water flowing in these stream channels, Sand is usually transported and deposited in the channel or next to the channel. And it's really not until that channel becomes abandoned and a new channel forms that this kind of forms a lake type environment that becomes filled eventually with mud. And that mud then can act as a vertical barrier to fluid communication between sand bodies. So we call these mud plugs, and they're impermeable. And this one here might separate this body from that body, and so on. The scale of these features can be large or they can be very small. But there's something that when you're drilling wells in fluvial point bar, meandering river type reservoirs, it's something that you're going to find, and it's something that can really very highly compartmentalize your reservoir and cause you to have to drill more wells or different types of wells. So I go back to this diagram again, and just to run through it quickly, again, the different type of environment is going to give you different degrees of uncontacted reservoir sand. Like that I showed before. So, you need to know your depositional system for your reservoir. Now, you all know what porosity and permeability is, just to show. This is porosity that is unconnected, individual pores shown in black that are not connected. So you might have a reservoir here of high porosity but low permeability. Here, permeability is measured by the rate of flow of fluid through a sand, like a cork plug. So you inject fluid here, and then it comes out here, and this may be the travel path, very tortuous travel path, as the fluids go between the pore spaces. And so you measure you can measure both of these properties, and like I said before, in particular, permeability varies with grain size and even after cementation. So once again, I really like this diagram that shows that effect, and when you're upscaling, why you want to try to minimize the upscaling of these properties, particularly the permeability. Why don't we take a short break, all right, about 10 minutes to get up and stretch and